How can cloud seeding be used to prevent wildfires, regenerate forests, refill water reservoirs, and irrigate agricultural lands? Cloud seeding, a weather modification technique, involves dispersing substances into the atmosphere to encourage cloud condensation and precipitation. By enhancing rainfall, cloud seeding can play a significant role in preventing wildfires, regenerating forests, refilling water reservoirs, and irrigating agricultural lands. Here's how cloud seeding can be applied in each of these areas. 1. Preventing wildfires. Objective: increase rainfall to dampen vegetation and reduce the likelihood of wildfires. Method: deploy cloud seeding aircraft or ground-based generators to release seeding agents like silver iodide, potassium iodide, or sodium chloride into clouds. Target specific areas prone to wildfires during dry seasons. Outcome: increased rainfall raises soil moisture and humidity levels, making vegetation less prone to ignition. 2. Regenerating forest. Objective: enhance rainfall to support forest growth and recovery, particularly after deforestation or wildfires. Method: implement cloud seeding in regions where forest regeneration efforts are ongoing. Coordinate with reforestation projects to ensure optimal timing for seedling growth. Outcome: adequate rainfall ensures young trees and seedlings receive the necessary water for growth, aiding in faster forest regeneration. 3. Refilling water reservoirs. Objective: increase water levels in reservoirs, ensuring a stable water supply for various needs. Method: target cloud seeding operations over catchment areas and watersheds feeding into reservoirs. Use meteorological data to identify optimal cloud conditions for seeding. Outcome: enhanced precipitation contributes to higher water inflows into reservoirs, improving water storage for municipal, industrial, and agricultural use. 4. Irrigating agricultural lands. Objective: ensure sufficient rainfall to support crop growth and productivity. Method: focus cloud seeding efforts on agricultural regions experiencing drought or insufficient rainfall. Schedule seeding operations during critical growing periods to maximize crop yield. Outcome: increased and more reliable rainfall helps maintain soil moisture levels, reducing the need for supplemental irrigation and supporting healthy crop growth. Implementation and considerations. Meteorological assessment: conduct thorough weather analysis to identify suitable clouds for seeding. Use advanced weather models and satellite data to optimize seeding operations. Environmental and health safety: use seeding agents that are safe for the environment and public health. Monitor and evaluate the ecological impact of cloud seeding activities. Coordination with local authorities: collaborate with government agencies, environmental organizations, and local communities. Ensure cloud seeding operations are integrated with regional water management and disaster prevention plans. Cost and infrastructure: assess the cost-effectiveness of cloud seeding relative to other water management and fire prevention methods. Develop the necessary infrastructure, including aircraft, ground generators, and monitoring equipment. Monitoring and evaluation: establish a system to monitor the effectiveness of cloud seeding in achieving desired outcomes. Continuously evaluate and adapt strategies based on observed results and changing environmental conditions. Conclusion: cloud seeding offers a proactive approach to managing water resources and mitigating wildfire risks. By strategically enhancing rainfall, it can support forest regeneration, maintain water reservoirs, and ensure the sustainability of agricultural lands. However, successful implementation requires careful planning, coordination, and monitoring to address environmental, logistical, and financial challenges. Cloud seeding to prevent wildfires occurring more frequently. A method of modifying the weather called cloud seeding entails releasing chemicals into the atmosphere to promote the development of clouds and precipitation. This method may be used to lessen wildfire frequency and intensity, especially in regions that are vulnerable to dry weather and drought. Here's how reducing wildfires using cloud seeding may work. How cloud seeding works: seeding agents: substances like silver iodide, potassium iodide, or sodium chloride are dispersed into clouds. Cloud formation: these particles act as nuclei around which water droplets can form. Precipitation induction: the increased number of droplets coalesce to form larger droplets, which then fall as rain or snow. Potential benefits for wildfire reduction: increased precipitation, moisture for vegetation, Increased rainfall can provide much-needed moisture to vegetation, reducing its susceptibility to ignition. Soil moisture. Higher soil moisture levels can help prevent the drying out of grasses and shrubs, which are common fuel sources for wildfires. Humidity levels. Higher humidity. Cloud seeding can increase the humidity levels in the air, making it more difficult for fires to start and spread. Evapotranspiration. Moisture from precipitation can reduce the drying effects of evapotranspiration in plants, maintaining healthier, more fire-resistant vegetation. Reducing drought conditions. Alleviating drought. In drought-prone areas, cloud seeding can provide relief by increasing precipitation, reducing the overall drought stress on ecosystems. Reservoir levels. Enhancing precipitation can help maintain water levels in reservoirs, ensuring a more reliable water supply for firefighting efforts. Challenges and considerations. Effectiveness. Variable results. The effectiveness of cloud seeding can vary based on geographic location, cloud conditions, and atmospheric parameters. Scientific debate. Some studies suggest that while cloud seeding can increase precipitation, the overall impact on a large scale and over the long term remains debated. Environmental and health concerns. Chemical use. The environmental impact of seeding agents like silver iodide needs careful consideration. While generally considered safe in the quantities used, potential long-term effects are still studied. Ecosystem balance. Introducing additional moisture in specific areas could potentially disrupt local ecosystems if not managed carefully. Logistical and economic factors. Cost. Cloud seeding operations require significant investment in technology and ongoing operational costs. Deployment. Effective cloud seeding requires the right weather conditions, as well as infrastructure such as aircraft or ground-based generators to disperse the seeding agents. Conclusion. Although it offers a viable way to boost precipitation and maybe lower the frequency and intensity of wildfires, cloud seeding is not a standalone remedy. It ought to be viewed as a component of a more comprehensive integrated strategy for managing wildfires, which consists of forest management, controlled burns, thinning of forests, and removal of dead trees. Firefighting resources, adequate funding, training, and equipment for firefighting personnel. Community preparedness, educating communities on fire prevention and creating defensible spaces around properties. Climate adaptation, addressing the underlying causes of increased wildfire risk, such as climate change and land use practices. These tactics, when paired with cloud seeding, can increase overall wildfire resistance. To optimize its advantages and mitigate any possible drawbacks, more investigation and prudent use are needed.